Before we begin, take a quiet moment to settle in. If you enjoy drifting through the universe with calm stories like this, you're warmly invited to subscribe. It helps this channel continue creating peaceful journeys you can return to night after night. Now, let your breathing slow. Far beyond the familiar glow of our sun, there exists a kind of star so vast that the word size begins to lose its meaning. A star whose surface could swallow the orbits of planets, whose light travels across distances that feel almost unreal, yet whose presence is silent, steady, and strangely gentle. Tonight, we are not here to be frightened by the universe. We are here to rest inside it. As we move slowly through this story, we'll explore the biggest star ever found, not as a threat, not as a catastrophe, but as a reminder of how quietly powerful the cosmos can be. There will be no rush, no sharp turns, only a gradual unfolding of scale, light, and calm understanding. So allow the outside world to fade. Let the weight of the day loosen its grip, and together, let's drift toward a star so immense that even fear dissolves into wonder. Chapter 1. What a star truly is when size loses meaning. When we hear the word star, the mind often reaches for something familiar, a small point of light, a steady glow in the night sky, something distant, beautiful, and safely contained within imagination. But the universe does not think in human proportions. Out here, size is not measured by what feels reasonable, but by what gravity allows, by how much matter can gather before balance gives way to collapse or fire. To understand the biggest star ever found, we must first release the idea that a star is simply a brighter version of our Sunday. Our sun feels immense because it is close. It warms our skin from nearly 150 million kilometers away. Its gravity binds planets, asteroids, comets, and dust into a slow, elegant dance. Compared to Earth, it is overwhelming. Compared to us, it is absolute. Yet in the deeper universe, the sun is quiet, modest, almost humble. There are stars so large that if they were placed where our sun now rests, their outer atmosphere would stretch far beyond the orbit of Mars, past Jupiter, perhaps even brushing against Saturn's distant path. Not solid surfaces, not burning ground, but vast oceans of plasma, billowing layers of glowing gas, expanding and contracting like a cosmic breath. These stars are not points of light, they are volumes, regions of space where matter itself glows. To imagine them, picture this. If the sun were the size of a small dot on a page, some of these stellar giants would fill the entire room around you. Walls, ceiling, floor, all immersed within a single star's outer layers. And yet, despite their scale, they are astonishingly delicate. The largest stars are not dense fortresses of matter. They are, in many ways, fragile. Their outer layers are thin, loosely bound, held together by gravity that must stretch itself across unimaginable distances. A gentle stellar wind can peel away entire regions of a star's atmosphere, sending glowing gas drifting into space like luminous fog. Size, in the universe, does not mean strength in the way we expect. It means tension, balance, a constant negotiation between collapse and expansion. At the heart of every star, no matter how large, there is a quiet struggle. Gravity pulls inward, endlessly patient, trying to compress matter into tighter and tighter forms. At the same time, nuclear fusion pushes outward, releasing energy as atoms merge, creating light, heat, and pressure that resist collapse. In small stars, this balance is firm and stable. In stars like our sun, it can last for billions of years. But in the biggest stars ever found, this balance is stretched thin. Their cores burn fuel at astonishing rates. They shine not gently, but extravagantly. Each second, they release more energy than our sun will emit across days, weeks, or even years. And yet, they are often cooler at the surface. This is one of the universe's quiet paradoxes. A star can be unimaginably powerful at its core, while appearing calm and dimmer at its edges. The energy must travel such vast distances through layers of plasma that it spreads out, softens, arriving at the surface as a warm, diffuse glow rather than a blinding blaze. These giants often glow red or orange, their light stretched toward longer wavelengths, their surfaces swelling outward like slow-motion tides. They do not flicker, they do not sparkle, they loom. To astronomers, discovering such stars was not straightforward. From Earth, even the largest stars appear as points. Distance erases scale. A star 1,000 times larger than the Sun can look identical to a star much smaller if it lies far enough away. Understanding size requires patience, mathematics, and indirect vision. Scientists learn to read subtle clues: how a star's light spreads across different wavelengths, how it brightens and dims over time, how surrounding gas responds to its presence. From these faint signals, a picture slowly emerges. Not an image, but a measurement, a realization. Some stars were simply too big. Their calculated diameters exceeded what theory once considered possible. Their mass loss rates suggested enormous, unstable envelopes. Their luminosity hinted at cores burning through fuel at reckless speeds. At first, these measurements felt unreal. Errors, perhaps. Artifacts of distance or dust. But as more data arrived, as different telescopes confirmed the same conclusions, the truth became unavoidable. The universe had built stars on scales far beyond our intuition. Among these giants are objects so vast that even describing them feels like exaggeration. Yet they exist, quietly, patiently. For now, it is tempting to call such stars terrifying. Their energy output dwarfs anything humanity has ever produced. Their eventual deaths can reshape entire regions of space. But terror is a human response. The stars themselves are not violent by intention. They follow physics. They obey balance until balance is no longer possible. In their daily existence, they are serene. From within their extended atmospheres, there is no explosion, no chaos. Only slow circulation of plasma, gentle convection currents larger than entire planetary systems, and steady streams of light flowing outward. If you could stand somewhere within the outer layers of such a star, not that standing would mean anything there, you would not feel sudden destruction. You would feel warmth, pressure, a constant glow without edges. The concept of a surface becomes meaningless. These stars do not end abruptly. They fade outward, layer by layer, until gas becomes thin enough to merge with the surrounding space. They blur into the universe. And in this blurring, they teach us something subtle, that the largest things are not always sharp. That power does not require violence. That scale, when taken far enough, becomes softness. Even gravity, stretched across these distances, becomes gentle. This is why the biggest stars often live fast and briefly. At least by cosmic standards, they are burning their lives outward, spreading themselves thin across enormous volumes, losing mass with every passing moment. Each breath of stellar wind carries away pieces of the star's identity, enriching surrounding space with heavier elements, the raw material for planets, moons, and eventually, life. In this way, even their excess becomes a gift. The universe does not waste scale. Every oversized star is a reminder that creation is not optimized for permanence, but for transformation. As we continue this journey, we will look more closely at how astronomers found these stars, how they measured what cannot be seen, and how the largest star ever discovered fits into this grand pattern. But for now, let this idea settle gently. Somewhere in the vast darkness, there exists a star so large that it redefines what big means. And yet, it burns quietly, slowly dissolving into space, unaware of our awe, untroubled by our fear, just glowing, just existing. And in its silent balance, it invites us to release our own sense of urgency, to remember how small worries become when measured against the calm patience of the cosmos. Chapter 2. How astronomers discovered stars beyond comprehension. Long before astronomers could name the biggest stars, they first had to accept a quiet truth. The universe rarely reveals its extremes directly. The largest stars were not discovered in moments of sudden revelation, but through patience, through subtle inconsistencies, through light behaving in ways that refused to fit familiar patterns. To find something unimaginably large, scientists had to learn how to measure what could never be touched. At first glance, every star looks the same, a distant spark, a single pixel against blackness. No matter how powerful a telescope becomes, distance flattens scale. A star twice the size of the sun, and a star 1,000 times larger, can appear identical if the larger one is far enough away. So astronomers learned to listen instead of look. They began with light. Light carries memory. It remembers where it has been, what it passed through, what forces shaped it on its journey. When starlight reaches Earth, it arrives stretched, filtered, softened by dust, gas, and distance. But hidden inside that light are patterns, spectral fingerprints that reveal temperature, composition, motion, and size. By splitting starlight into its component colors, scientists could see which elements were present: hydrogen, helium, heavier metals. Each leaves a distinct signature. But size required a different kind of reasoning. Brightness alone could not tell the full story. A small star nearby can appear brighter than a massive star far away. Distance had to be known. And distance, for much of history, was one of astronomy's greatest challenges. Then came parallax, the gentle shift in a star's position as Earth moves around the sundial. Tiny, almost imperceptible movements that, when measured carefully, revealed how far away a star truly was. With distance known, brightness transformed into luminosity. Not how bright a star looks, but how much light it actually produces. And this is where things began to feel strange. Some stars were too luminous, far too luminous for their measured temperatures. They radiated enormous amounts of energy, yet their surfaces were relatively cool. Red, orange, swollen. The only explanation was size. If a star is cool but extremely bright, it must be vast, its surface area enormous enough to compensate for lower temperature. By sheer scale, these stars were not burning hotter, they were burning wider. As astronomers refined their measurements, they noticed another clue: variability. Many of the largest stars breathe. They expand and contract slowly, their brightness rising and falling over months or years. Not violently, not erratically, but rhythmically. These pulsations are not surface flickers. They are structural movements. The star's entire outer envelope, swelling and relaxing. As internal forces shift, by timing these pulsations, scientists could infer internal properties, including size and density. Some of these rhythms were so slow that a single cycle could last years, a quiet, cosmic heartbeat. And then there were stellar winds. The largest stars lose mass continuously, not in explosions, but in steady flows. Their gravity, stretched thin across immense distances, struggles to hold on to their outer layers. Radiation pressure pushes outward, carrying gas away into surrounding space. By observing how much material was escaping, astronomers could estimate how extended the star must be for such loss to occur. Again and again, the numbers pointed upward, bigger, larger, more expansive than models had predicted. At first, these discoveries challenged long-held assumptions. There were limits, scientists believed. Stars could not grow beyond certain sizes, without becoming unstable, without tearing themselves apart. And yet, the universe had quietly crossed those boundaries. Some of the biggest stars ever found reside in distant regions of our galaxy, or in neighboring galaxies where conditions differ subtly from our own. Environments rich in gas, with slightly different chemical compositions, can give rise to stars that grow unusually large before stabilizing, if only briefly. Dust clouds collapse. Gravity gathers material. Rotation, pressure, and temperature negotiate a temporary truce, and a giant is born. One of the most astonishing moments in stellar astronomy came when measurements began to converge around stars whose diameters defied comprehension. Stars so large that if placed at the center of our solar system, their surfaces would extend beyond the orbit of Jupiter, approaching Saturn's distant ring of motion. Not hypothetical objects, measured, confirmed. Yet even then, caution remained. Astronomy is a science of humility. Every conclusion carries uncertainty. Distances can be revised. Dust can deceive. Models evolve. So scientists cross-checked. Interferometry allowed telescopes to work together, combining their light to resolve details that single instruments could not. Subtle differences in starlight arriving at separated observatories revealed hints of stellar size. Infrared observations pierced through dust, revealing stars hidden from visible light. Some of the largest stars shine most clearly, not in optical wavelengths, but in infrared glow, warm, diffuse, and revealing. With each new technique, the picture sharpened. The universe was not merely capable of producing giant stars, it seemed to prefer them, at least under the right conditions. And yet, even as their sizes grew, another realization followed. These stars were rare, exceptionally rare. They represent fleeting moments. In cosmic time, while small stars can live for tens or hundreds of billions of years, the largest stars burn through their fuel with astonishing speed. Millions of years, sometimes less. In a universe nearly 14 billion years old, that is a blink. To find one is to catch a moment already passing. This is why the biggest stars ever found often sit surrounded by clouds of gas and dust, the remnants of their own formation, or the material they are actively shedding. They are transitional beings, neither stable nor chaotic, balanced only temporarily. In discovering them, astronomers were not just finding objects, they were witnessing processes. Birth stretched to its extreme, existence pushed to its limits. And this understanding shifted something deeper. The universe was no longer a place of tidy categories. Small stars, medium stars, large stars. Instead, it revealed itself as a spectrum, a continuous range of possibility, bounded not by neat rules, but by delicate balances. Gravity allows growth. Radiation resists it. Rotation shapes it. Environment nudges it. Where these forces align just right, a star can become enormous. Not violent by design, not monstrous by intent, just large. And as astronomers catalogued these giants, another quiet lesson emerged. The universe does not aim for efficiency. It explores. It tests extremes. It allows structures to form, even if they are short-lived, even if they are unstable, even if they exist only briefly, before transforming into something else. In that sense, the biggest stars ever found are not anomalies. They are experiments, natural expressions of what matter can do when given enough time, space, and freedom. As we continue deeper into this journey, we will explore what these stars are truly made of, how their internal structures differ from smaller stars, and why their immense size carries the seeds of their own endings. But for now, let this thought drift gently. Somewhere far away, light left a giant star millions of years ago, crossed interstellar space, slipped through dust and gas, and finally arrived at Earth as a faint signal. From that whisper of light, human minds learned that the universe builds bigger than imagination, and does so quietly, without announcement, without urgency, just patiently revealing itself to those willing to listen long enough. Chapter 3. The structure of the biggest stars ever found. To understand the biggest stars ever found, we must turn inward. Not inward toward ourselves, but inward toward the quiet interiors of these stellar giants, where forces beyond everyday intuition hold matter in a delicate, shifting balance. From the outside, a massive star appears calm, a glowing sphere, a steady presence against darkness. But inside, everything is moving, not rushing, not exploding, moving. At the very center of the largest stars lies a core unlike anything we can touch or recreate. Temperatures rise into tens of millions of degrees. Pressure climbs beyond comprehension. Atoms are pressed so closely together that they begin to merge. This is nuclear fusion, the process that allows stars to shine. In smaller stars, like our Sun, fusion proceeds slowly and methodically. Hydrogen atoms fuse into helium, releasing energy in a steady, controlled flow that can last for billions of years. In the biggest stars, fusion is impatient. Their immense gravity compresses the core so intensely that fuel burns at staggering rates. Hydrogen does not linger. It is consumed quickly, converted into heavier elements in a cosmic furnace that rarely rests. Yet, despite this ferocity at the center, the star does not explode outward. Why? Because every outward push is met by gravity's inward pull. This balance is called hydrostatic equilibrium, a quiet stalemate between collapse and expansion. In giant stars, this equilibrium is fragile, not broken, but stretched. Energy produced in the core must travel outward, passing through vast layers of plasma. Along the way, it is absorbed, re-emitted, scattered, and softened. By the time it reaches the outer layers, that fierce core energy becomes warmth, glow, a gentle radiance that belies its origin. Surrounding the core are zones where energy moves in different ways. In some regions, radiation carries energy outward, photons bouncing endlessly through dense matter, taking thousands of years to escape. In other regions, convection dominates. Hot material rises, cooler material sinks. In the largest stars, these convective cells can be unimaginably large, each one spanning distances greater than the orbit of Earth. The surface we see is not smooth. It is alive with slow, rolling motion, like a vast, glowing ocean viewed from above. And beyond this surface lies something even stranger. The outer layers of the biggest stars are not firmly attached. Gravity weakens with distance, and in these giants, the distance is enormous. Radiation pressure, the gentle but persistent push of light itself, begins to matter. Photon by photon, light pushes outward, nudging gas away from the star. Stellar winds form, not gusts, not blasts. Continuous outflows of material, streaming into space, carrying away mass at astonishing rates. Some of the biggest stars lose the equivalent of Earth's mass every few years. Others lose far more. This mass loss shapes their evolution. As the star sheds its outer layers, its internal balance shifts. Fusion rates change. Structure adjusts. The star is slowly rewriting itself. Inside these giants, fusion does not stop at helium. As hydrogen is exhausted in the core, the star adapts. Helium begins to fuse into carbon and oxygen. Later, heavier elements form: neon, magnesium, silicon. Each stage burns hotter and faster than the last. Each stage lasts for a shorter time. The biggest stars live their lives in accelerated motion. What might take a small star billions of years can occur in a giant in mere millions. This layered structure, like an onion made of fire, is one of the defining features of massive stars. An iron core eventually forms at the center, and iron is special. Fusing iron does not release energy. It consumes it. At that point, the quiet balance that held the star together can no longer be maintained. But that ending lies far ahead in our journey. For now, we remain in the present life of the giant. The vast size of these stars creates effects that smaller stars never experience. Rotation, for example, plays a subtle but important role. As a massive cloud collapses to form a star, any slight rotation becomes amplified. Conservation of angular momentum ensures this. In the biggest stars, rotation can be rapid enough to flatten the star slightly at the poles, creating an oblate shape. This rotation influences how material moves inside, how fusion proceeds, and how mass is lost into space. Magnetic fields weave through these structures, guiding charged particles, shaping stellar winds, and contributing to surface activity. Yet even here, the violence is subdued. There are no flares like those seen on smaller, more active stars. No sharp bursts of radiation. Everything happens on enormous scales, over long times, with smooth transitions. If our sun is a flickering candle, a massive star is a glowing fog bank. Light without edges, heat without sharpness. And because their outer layers are so diffuse, the largest stars can appear unstable, their boundaries shifting, their surfaces breathing. Some expand and contract over years. Others experience episodes of enhanced mass loss, shedding shells of gas that drift outward and glow softly under the star's light. These shells can form complex, beautiful structures, rings, arcs, and filaments that surround the star like echoes of its own existence. To astronomers, these structures are clues, records of what the star has been, and hints of what it will become. To us, they are reminders that even the most massive objects are not fixed. They change, they adapt, they age. Size does not grant permanence. In fact, in the universe, size often shortens life. The biggest stars live intensely, burning brightly and briefly, transforming themselves rapidly. But intensity does not mean chaos. It means commitment. Every moment of a giant star's life is spent converting matter into energy, energy into motion, motion into structure, and in doing so, it seeds the cosmos with elements that smaller stars could never produce alone. Carbon for life, oxygen for breath, iron for planets. These materials are forged not quietly, but inevitably, as part of the star's internal journey. When we look at the biggest stars ever found, we are not just observing enormous balls of gas. We are witnessing the universe, learning how to build complexity, learning how to recycle, learning how to turn raw hydrogen into the ingredients of worlds. As we drift deeper into this story, we will explore what happens when these giants reach the limits of balance, what their immense size means for their endings, and how those endings shape galaxies. But for now, let the image settle. A star so large that its interior contains entire solar systems worth of space, yet so delicately balanced that light itself can push matter away. A being of fire and softness, power and fragility, existing for a brief moment in the long, patient life of the universe. Just glowing, just transforming, just quietly becoming something new. Chapter 4. Tension, not collapse. When new observations arrive, especially ones that reach farther back in time than ever before, it is tempting to think in absolutes. Either a theory stands, or it falls. But science rarely moves in such sharp motions. It stretches, it adjusts, it breathes. The discoveries made by the James Webb Space Telescope did not strike cosmology like a sudden crack of thunder. They arrived more like a slow change in the weather, noticeable only to those who were paying close attention. Galaxies appearing earlier than expected, brighter than predicted, more massive than models had comfortably allowed. These findings created tension, but not panic. To understand why, we must pause and consider what the Big Bang Theory actually is, and what it is not. The Big Bang is not a detailed blueprint for every galaxy, star, and planet. It does not specify how quickly each structure must form, or how efficiently matter must organize itself. Instead, it describes the universe's earliest state and its large-scale evolution. It explains why space is expanding, why distant galaxies are moving away from us, why the universe is filled with a faint, uniform glow of ancient radiation, why hydrogen and helium dominate cosmic matter. These pillars remain untouched. James Webb did not observe a universe that is not expanding. It did not detect a background radiation inconsistent with predictions. It did not find elemental abundances out of place. What it revealed lies after the beginning, in the era when gravity took over and matter began to assemble. This is where uncertainty has always lived. Galaxy formation is one of the most complex problems in modern astrophysics. It involves gravity, gas dynamics, radiation, turbulence, magnetic fields, and the invisible scaffolding of dark matter. Small changes in any of these processes can produce large differences in outcomes. For decades, scientists relied on simulations to fill the gaps left by observation. These simulations were not guesses. They were carefully constructed models based on known physics. But models, by their nature, must simplify. They approximate feedback processes. They average behaviors. They make assumptions about efficiency and timing. James Webb offered a chance to test those assumptions against reality, and reality responded with nuance. Some early galaxies, it turned out, may have formed stars more efficiently than previously assumed. Gas clouds might have cooled faster. Star formation might have proceeded in intense bursts rather than gradual waves. In dense regions of the early universe, dark matter halos could have collapsed quickly, drawing gas inward with surprising speed. If even a few of these processes operated slightly differently, the timeline shifts. Not dramatically, but enough to matter. What once required 1 billion years might only need a few 100 million. From a human perspective, this feels enormous. From a cosmic perspective, it is subtle. There is also the question of interpretation. When astronomers infer the mass of distant galaxies, they do so indirectly. They measure light. They analyze spectra. They model stellar populations. These methods depend on assumptions about how stars form, how bright they are at different ages, and how dust absorbs light. If early stars behaved differently, if they were more massive, hotter, or shorter-lived, then mass estimates could shift. What appears to be a mature galaxy might be a younger system, burning unusually bright. This possibility is not an escape route. It is a reminder of humility. We are interpreting ancient light through layers of theory and inference. Webb has sharpened the image, but interpretation remains a human task. There is also the role of selection. The first galaxies Webb observed were among the brightest and most massive of their time. These are the ones easiest to detect. Fainter, smaller galaxies, perhaps far more numerous, remain below the detection threshold. Our early view of the young universe may be biased toward its most extreme examples. Seeing only the tallest trees does not mean the forest was entirely made of giants. As more data accumulates, a fuller picture begins to emerge. Some early galaxies were indeed massive and structured. Many others were not. The universe, as always, was diverse. This brings us to an important truth, often missed outside scientific circles. Tension between theory and observation is not a flaw. It is the engine. When predictions and data disagree, scientists do not discard frameworks lightly. They investigate the mismatch. They ask where assumptions may be too rigid, where parameters may be too narrow, where physics may be incomplete. Sometimes this leads to minor adjustments, sometimes to major breakthroughs. But collapse is rare. The Big Bang itself was once such a tension. Before it was widely accepted, observations of galaxy redshifts did not align with a static universe. The idea of expansion challenged long-held beliefs. It took decades of evidence to reshape consensus. Now, the process repeats, not at the foundation, but in the details. There are even more speculative ideas being discussed quietly. Could dark matter behave differently in the early universe? Could interactions between radiation and matter be more complex than we thought? These questions are explored cautiously, not as declarations, but as possibilities. No single observation rewrites cosmology. Patterns matter. Consistency matters. And so far, the pattern remains coherent. A universe that began hot and dense, expanded and cooled, formed structure under gravity. What Webb has shown is that this process may have been more efficient, more dynamic, more creative than our earlier models suggested. This does not weaken the story. It enriches it. There is a quiet beauty in this moment. We are witnessing science in motion, not as conflict, but as conversation. Data speaks. Models respond. Understanding deepens. The universe is not defending itself. It is not arguing. It is simply revealing what has always been there. And as we listen more carefully, we begin to appreciate that certainty is not the goal. Clarity is. In the final part of our journey, we will step back and reflect on what this moment teaches us. Not just about the universe, but about how knowledge itself evolves. Because sometimes, the most profound discoveries are not those that shatter our beliefs, but those that gently remind us how much more there is to learn. Chapter 5. How Science Grows in Silence. When the universe offers new information, it rarely does so with urgency. There are no announcements written across the sky, no signals meant to persuade or convince. There is only light, ancient, patient, carrying the quiet memory of distant events. Science exists to listen to that light, not to rush toward conclusions, but to sit with uncertainty long enough for patterns to emerge. The discoveries made by the James Webb Space Telescope have reminded us of this discipline. They have not overturned our understanding of the universe's beginning. They have deepened our appreciation for how complex the path from simplicity to structure truly is. In this sense, the story unfolding now is not about the Big Bang itself, but about what came next, about the first billion years, a span of time so vast that human language struggles to contain it, yet so brief in cosmic terms that entire galaxies seem to have grown in its shadow. Science advances by layering insight upon insight. The Big Bang theory did not appear fully formed. It was shaped over decades by observation, debate, refinement, and doubt. It survived, not because it was protected, but because it consistently aligned with reality. Each new instrument added detail. Each new survey tested its limits. James Webb is simply the latest voice. In a long conversation between humanity and the cosmos, what makes this moment special is not the challenge itself, but the way it is being met. Astronomers did not rush to declare victory or defeat. They examined their tools, rechecked calibrations, expanded sample sizes. They asked whether brightness truly meant mass, whether early stars behaved differently, whether unseen populations of faint galaxies balanced the apparent excess of large ones. This patience is not hesitation. It is respect. Respect for the complexity of nature. Respect for the limits of interpretation. Respect for the fact that knowledge grows, most reliably when allowed to breathe. There is a common misconception that science moves in sudden revolutions. Old ideas destroyed, new ones crowned overnight. Reality is quieter. Most progress comes from small corrections, from narrowing uncertainties, from recognizing where models oversimplify reality. In this case, the Big Bang remains the opening chapter, but the early pages that follow are being rewritten with finer detail. The universe, it seems, was more capable than we imagined. It could organize itself quickly under the right conditions. It could produce light, structure, and complexity without waiting for long, drawn-out timelines. This realization does not diminish the wonder. It increases it. A universe that can build galaxies so swiftly is a universe rich with possibility. And that possibility extends beyond cosmology. The way we respond to these discoveries reflects something fundamental about human curiosity. We are not searching for comfort. We are searching for truth. And truth is rarely simple. It unfolds gradually, often contradicting expectations, without contradicting reality. There is also humility in this process. Every generation of scientists inherits a partial picture. They refine it, extend it, and pass it forward. James Webb will not be the final word. Future telescopes, even more sensitive, even more precise, will continue the conversation. They will look deeper, see fainter, measure more accurately. Some ideas will be strengthened, others will soften. A few may quietly fade away. This is not failure, it is growth. In a sense, science mirrors the universe it studies. It expands, it cools, it organizes itself over time. Errors are not explosions, they are corrections. Misunderstandings are not collapses, they are invitations. The universe does not demand certainty from us, only attention. And so, as we reflect on what James Webb has shown us, we can rest in a simple understanding. The Big Bang was not broken. It was clarified. The universe's story has not ended. It has become richer, more nuanced, more alive. We now see that the early cosmos was not a slow, hesitant place, but a dynamic environment, where gravity, light, and matter work together with remarkable efficiency. This knowledge does not close doors. It opens them. It invites new questions about dark matter, about the nature of early stars, about the speed at which order can arise. And it reminds us that the universe is not obligated to match our expectations. It exists as it is, patient, vast, unconcerned with human timelines. As listeners to its story, our role is not to rush ahead, but to follow gently, adjusting our understanding as needed. In the quiet orbit where James Webb listens, there is no urgency, only light arriving, one photon at a time, each carrying a fragment of a story, older than Earth itself. As this journey draws to a close, we are left not with answers carved in stone, but with a deeper calm, a sense that knowledge is not something we conquer, but something we approach, slowly, carefully, with wonder. And in that calm, perhaps the greatest discovery of all emerges. The universe is not fragile. Our theories are not brittle. They are living frameworks, growing alongside our ability to see. And as we rest beneath the quiet sky, we can take comfort in knowing that every new question brings us closer to understanding our place within this vast, unfolding cosmos. Chapter 6. Listening to what comes next. When a discovery settles, when the first waves of excitement fade, what remains is something quieter and far more important: attention. The universe does not reveal itself all at once. It speaks in fragments, in faint signals, in patterns that only emerge after long periods of listening. James Webb has begun a conversation, not a conclusion. Its early observations have reminded scientists that the first billion years of cosmic history were not merely a prologue, but a complex chapter filled with rapid change, hidden efficiency, and unexpected maturity. Yet this chapter is still being read. Every observation raises new questions. Every answer opens another door. If galaxies formed earlier than expected, what conditions made that possible? Was dark matter more influential in the early universe than our models assume? Did gas cool faster due to unknown mechanisms? Were the first stars fundamentally different from those that formed later? These are not dramatic mysteries. They are precise ones. And precision is where science thrives. In the coming years, James Webb will continue to stare into the past, targeting galaxies even closer to the moment when the first stars ignited. It will measure their spectra more carefully, estimate their masses with greater accuracy, separate light from stars, gas, and dust with increasing confidence. Patterns will begin to form. Some early claims will soften, others will strengthen. The universe will clarify itself, not because it is changing, but because we are learning to see more clearly. This is how progress happens, not in leaps, but in refinement. There is also a broader shift underway. Cosmology is moving from a field limited by observation to one guided by abundance. For the first time, astronomers are not struggling to find early galaxies. They are struggling to understand the sheer number of them. This abundance changes perspective. Instead of asking, can galaxies form this early? We begin to ask, how common was this process? Instead of focusing on anomalies, we search for distributions. The early universe becomes less mysterious and more statistical, and with statistics comes stability. Extreme examples no longer dominate the story. They find their place within a broader context. The universe stops feeling surprising and starts feeling consistent again, not because it matches old expectations, but because new expectations take shape. This process is ongoing, and it is deeply human. We build instruments. They show us something unexpected. We pause. We adapt. At no point does the universe rush us. It has waited billions of years to be observed. It will wait longer still to be understood. There is a quiet lesson in this patience. Knowledge does not demand certainty. It rewards curiosity. The Big Bang Theory, like all strong scientific frameworks, has endured not because it resists change, but because it accommodates it. It has absorbed new data before: dark energy, accelerated expansion, inflation. Each addition did not weaken the theory. It made it more complete. James Webb's discoveries belong to this tradition. They do not rewrite the beginning. They enrich the middle. They remind us that the universe's earliest epochs were more active, more capable, and more complex than our early models allowed. And that is not a failure of imagination. It is its growth. As future observatories join this effort, radio telescopes mapping hydrogen across cosmic time, ground-based giants peering deeper into infrared, space missions refining cosmic background measurements, the picture will continue to sharpen. What feels uncertain now will feel familiar later. What feels surprising will become expected. This is not the end of a story. It is the settling of a rhythm. The universe began hot and dense. It expanded. It cooled. Structure emerged. Within that structure, variation flourished. Some regions moved faster, some slower. Some galaxies grew rapidly, others lagged behind. Together, they formed the cosmos we see today. In this light, the phrase "breaking the Big Bang" loses its power. Nothing has broken. Something has been understood more deeply. And perhaps that is the most comforting realization of all. The universe is not fragile. Our understanding is flexible. It bends without snapping. It adjusts without erasing. As we conclude this journey, we return to the quiet from which we began. A vast sky, ancient light, a universe that does not demand answers, only attention. Tonight, as you rest beneath that sky, whether clouded or clear, remember that every star you cannot see is still there. Every answer we do not yet have is still forming. The cosmos does not rush. Neither must we. We listen, we wait, and slowly, the story continues to unfold. Chapter 7. A beginning that keeps unfolding. When we speak of beginnings, we often imagine something fixed. A single moment, a clear line between before and after. A door that opens once, then closes forever. But the universe has never worked that way. Its beginning was not a point we can circle neatly, nor a chapter we can finish reading and set aside. It was the start of a process, one that has been unfolding ever since, quietly, patiently, across distances too large for intuition, and times too long for memory. What the James Webb Space Telescope has shown us is not that our story of the universe was wrong, but that it was incomplete in the way all early stories are. We understood the outline. Now we are learning the texture. The early universe was once imagined as a slow learner, hesitant, fragile, taking its time to find structure and rhythm. Webb has suggested something different, a universe that adapted quickly, that gathered itself with surprising confidence, that formed stars and galaxies, not reluctantly, but eagerly, as soon as conditions allowed. This does not make the universe feel chaotic. It makes it feel capable. In this light, the Big Bang is not diminished. It is reframed, not as a distant, explosive event, locked away in the unreachable past, but as the first breath in a long, continuous exhale. Everything we see today, every galaxy, every star, every atom in our bodies, is part of that same motion. The universe did not finish beginning. It is still becoming. This realization carries a quiet philosophical weight. If the universe could organize itself so quickly, if complexity could emerge so early, then perhaps order is not as rare as we once thought. Perhaps structure is not an exception, but a tendency, given space, given time, given simple rules. Gravity pulls, energy flows, patterns form. This is not just a cosmological insight. It is a reminder of how nature works at every scale, from galaxies assembling in the dark, to storms forming in an atmosphere, to thoughts taking shape in a human mind. Order does not arrive fully formed. It grows, sometimes faster than expected, sometimes slower, but always through interaction, through tension, through balance. The debate, sparked by Webb's discoveries, is not really about whether the Big Bang is correct. It is about how comfortable we are with uncertainty. Science, at its best, does not fear being wrong. It fears being rigid. The willingness to adjust, to say, "We did not know this yet," is not weakness. It is maturity. In that sense, cosmology today mirrors the galaxies it studies, still forming, still refining, still responding to new information. No single observation defines the whole. No single theory captures everything. Understanding emerges from accumulation, from comparison, from patience. James Webb is a powerful tool, but it is not an oracle. It shows us what is there. It does not tell us what to think. That responsibility remains ours. And so, scientists will continue their work, measuring, modeling, revising. Some early claims will fade into nuance. Others will grow stronger with time. The universe will remain vast enough to accommodate both surprise and consistency. For those of us listening from afar, there is comfort in this balance. We do not need final answers to feel connected to the cosmos. We need only curiosity. The stars above us tonight are not frozen relics. They are participants in an ongoing story. Light leaves them, travels for millions or billions of years, and arrives here, quietly, without urgency. We receive it not all at once, but moment by moment. In that way, understanding is like starlight. It does not rush. It accumulates. And perhaps that is the deeper lesson of this chapter in our exploration. The universe is not something to be solved. It is something to be accompanied. We walk beside it with our instruments, our equations, our questions. Sometimes we catch up to its rhythm. Sometimes we lag behind. But the journey continues. As this chapter draws to a close, we find ourselves not at an ending, but at a widening horizon. The beginning of the universe was not a fragile idea, waiting to be broken. It was a doorway, and beyond it lies a landscape, still revealing its depth. James Webb has opened our eyes to how much richness existed, even in the universe's youth. And in doing so, it has reminded us that every beginning contains more than we first imagine. The night sky has not changed. The stars still rise and set. The cosmos remains vast and calm. What has changed is our listening. We have learned to hear fainter signals, to sit longer with questions, to accept that understanding is a slow, shared journey. And so, we rest here for a moment, not with certainty, but with quiet wonder, because the universe is still speaking, and we are still learning how to listen. Chapter 8. The quiet meaning of an expanding story. There comes a moment in every long exploration when the questions begin to soften, not because they have all been answered, but because they have found their place. The discoveries of the James Webb Space Telescope have carried us to such a moment. What began as a technical observation, galaxies appearing earlier brighter, more structured than expected, has gradually unfolded into something deeper, not a crisis of cosmology, but a reminder of how understanding truly grows. When humanity first looked up at the night sky, the universe felt distant and unchanging. Stars seemed fixed, patterns eternal. Only much later did we learn that everything above us is moving, expanding, evolving. The Big Bang gave us a way to think about that motion, a beginning that explained why space stretches, why light reddens, why the universe carries a faint memory of its earliest heat. James Webb has not erased that beginning. It has brought us closer to what followed it, and in doing so, it has invited us to reflect not only on galaxies and stars, but on the nature of knowledge itself. There is a temptation, especially in modern times, to expect clean answers, clear victories, definitive endings. But the universe does not offer itself that way. It reveals layers. Each new instrument peels one back, only to show another beneath. What Webb has shown us is that the early universe was not merely waiting to become complex, it was actively becoming so. Structure did not hesitate. Light did not delay. Gravity did not stumble. As soon as conditions allowed, matter gathered. Stars ignited. Galaxies assembled. This does not contradict the Big Bang. It completes it. It tells us that a beginning does not determine how slowly or quickly a story must unfold, only what is possible. And possibility, it turns out, was abundant. This realization carries a quiet emotional weight. For centuries, we imagined the early universe as fragile, a delicate newborn cosmos, taking tentative steps toward structure. Now we see something else. A universe that was resilient from the start, capable of organizing itself with surprising confidence. There is something comforting in this. It suggests that order is not rare. That complexity is not an accident. Given the right conditions, the universe seems inclined to build. This inclination echoes far beyond astronomy. In every domain we study, from biology to climate to consciousness, we see the same pattern. Simple rules, repeated interactions, emerging structure. The cosmos is not a static machine. It is a process, and we are part of that process. The atoms in our bodies were forged in stars that formed long after the first galaxies, yet followed the same fundamental laws. Gravity pulled, energy flowed, patterns emerged. In that sense, learning more about the universe's youth is also learning something about ourselves. Not in a poetic way alone, but in a literal one. Our existence depends on the universe's ability to organize matter efficiently. If galaxies had formed too slowly, stars might not have lived long enough to create heavier elements. If structure had been delayed, there would be no planets, no chemistry, no life. The fact that galaxies formed early is not just a curiosity. It is part of the reason. We are here to notice it. This does not make the universe feel purposeful in a human sense, but it does make it feel coherent. The laws that shaped the first galaxies are the same ones that shape the present moment. They have not changed. Our understanding has, and that understanding will continue to change. As new data accumulates, some interpretations will sharpen, others will soften. The story will become less dramatic, but more accurate. This is often the fate of genuine discovery. The initial surprise fades, replaced by integration. What once felt disruptive becomes normal. This does not diminish its importance. It confirms it. James Webb's observations will eventually be absorbed into a refined picture of cosmic history. Textbooks will be updated, simulations improved, timelines adjusted. The Big Bang will remain, galaxy formation models will evolve, and the universe will continue to do what it has always done: exist, unconcerned with our interpretations. There is humility in this realization. We do not impose meaning on the cosmos. We extract it carefully, knowing it may change. Certainty is provisional. Curiosity is permanent. Perhaps this is why cosmology feels so calming when approached slowly. It reminds us that even our most fundamental ideas are not rigid. They are adaptable. They grow as we grow. The universe does not punish us for misunderstanding it. It simply waits. And when we build better tools, it shows us more. As we sit with these thoughts, the night sky becomes something different. Not a collection of distant objects, but a record of ongoing creation. Every point of light is a chapter still unfolding. Every discovery is a reminder that knowledge is not a destination, but a path. James Webb has taken us a little further along that path, not by shouting answers, but by offering evidence, not by breaking theories, but by inviting refinement. And in that invitation, there is peace. We are not late to understanding the universe. We are right on time, arriving at the pace our tools allow. The story of the cosmos will never be finished, but it will continue to reveal itself to those willing to listen quietly. And in that listening, perhaps the greatest insight emerges. The universe does not rush, neither should we. We learn, we adjust, we continue, just as the cosmos has done since its very first moments. Chapter 9. What it means to know a universe in motion. As our journey nears its end, the questions we carry feel different than when we began. They are no longer sharp or urgent. They are spacious. James Webb did not give us a final answer about the origin of everything. Instead, it offered something more enduring, a deeper relationship with uncertainty. To know the universe is not to hold it still. It is to understand it as movement. From the moment space began to expand, nothing has remained fixed. Galaxies drift apart. Stars are born and fade. Light stretches, quietly changing its color as it travels. Even our theories participate in this motion. They expand with new evidence. They cool as excitement settles. They reorganize as understanding deepens. The Big Bang theory itself has followed this path. It began as a radical idea, a universe with a beginning. Over time, it absorbed observations, weathered challenges, and grew more refined. Inflation was added. Dark energy entered the picture. Details sharpened. James Webb's discoveries are part of this same evolution. They do not stand apart from the theory. They move within it. To some, this may feel unsettling. We often want knowledge to feel complete. But completeness is not the same as truth. Truth, in science, is provisional. It holds until better evidence arrives. This is not weakness. It is strength. A rigid idea can shatter. A flexible one adapts. The universe we are learning about is not fragile. Neither is our understanding of it. There is also something deeply human in this process. We are creatures who ask questions, not because we expect certainty, but because curiosity is part of who we are. We look outward to understand inward. When we learn that galaxies formed early, that structure emerged quickly, we are reminded that complexity does not always need long delays. Sometimes, given the right conditions, remarkable things happen swiftly. This insight resonates beyond astronomy. In our own lives, growth does not always follow neat timelines. Understanding can arrive suddenly. Change can happen quickly. After long periods of quiet preparation, the universe mirrors this pattern. For millions of years after the Big Bang, little seemed to happen. Then, stars ignited, galaxies assembled, light transformed space. From stillness, activity emerged. James Webb has allowed us to witness that transition with unprecedented clarity. And yet, even now, much remains unseen. There are galaxies too faint to detect, processes too subtle to measure, interactions too complex to model fully. This is not a failure of observation. It is a reminder of scale. The universe is large enough to outpace our instruments, and it always will be. This realization does not diminish science. It grounds it. We are participants, not masters. Listeners, not authors. The cosmos speaks through light, and we interpret as best we can. Sometimes our interpretations change. The light does not. As future telescopes come online, as data accumulates, the picture will continue to sharpen. Early galaxy populations will be mapped, star formation histories refined, timelines adjusted. What now feels like a mystery will become a chapter with footnotes, and new mysteries will take its place. This cycle is not endless repetition. It is progress. Each turn of the spiral brings us closer to coherence. Not finality, but clarity. Perhaps this is the deeper lesson of cosmology in the Webb era. We are not seeking to lock the universe into a single explanation. We are learning how to stay open to what it reveals. Openness requires patience. It requires restraint. It requires comfort with ambiguity. These are not traits, often celebrated in a fast world, but they are essential when listening to something as vast as the cosmos. As we reflect on the phrase, breaking the Big Bang, it becomes clear how misleading it is. Nothing was broken. A perspective was expanded. The universe did not contradict itself. It showed us more of itself, and we adjusted accordingly. This is how understanding deepens, not through confrontation, but through conversation. The cosmos speaks. We listen. We respond with revised models, refined questions, and renewed curiosity. In this quiet exchange, there is beauty. Not dramatic beauty, but enduring beauty. The kind that does not fade. When excitement passes, as we prepare to rest our minds, to let the stars fade into dreams, we can carry one gentle truth with us. The universe is not finished explaining itself, and neither are we finished learning. There will always be more light arriving, more data to interpret, more stories to tell, and that is not something to rush. It is something to appreciate, because in a universe that never stops moving, the act of understanding is itself a form of motion, slow, careful, endlessly unfolding. Just like the cosmos, we are trying to know. Chapter 10. Resting inside an unfinished universe. As our journey gently comes to a close, we return to the quiet from which it began, not to silence, but to a deeper calm. After traveling billions of years through light and time, after listening to galaxies form and theories evolve, we find ourselves in a universe that feels less resolved and more welcoming. The James Webb Space Telescope did not give us certainty. It gave us perspective. It showed us that even our most foundational ideas are not rigid monuments, but living frameworks. The Big Bang was not a brittle story, waiting to be broken. It was the opening note of a long, evolving composition. What followed that note was not chaos, but creativity. Matter gathered, light ignited. Structure emerged sooner than expected, not because the universe rushed, but because it was ready. In this understanding, the early cosmos becomes something different, not a fragile newborn, but a capable beginning. This does not diminish the wonder of the Big Bang. It deepens it. A beginning that leads quickly to complexity, suggests a universe rich with potential, a universe whose laws invite structure rather than resist it. And those same laws still operate now, quietly shaping stars, guiding galaxies, and sustaining the delicate condition that allow us to exist. There is comfort in continuity. The processes that built the first galaxies are the same ones that shape the night sky above us. Nothing essential has changed, only our understanding. Science does not promise final answers. It promises better questions, and James Webb has delivered them. Questions about efficiency, about timing, about how quickly order can emerge from simplicity. These are not threatening questions. They are enriching ones. They remind us that knowledge grows best when curiosity remains gentle. There is a temptation, especially at the end of a story, to seek resolution, to close the book, to declare understanding complete. But the universe does not offer endings, only pauses, moments where we gather what we have learned and prepare to listen again. The story of the cosmos will continue long after us. New stars will form, old galaxies will fade. Light will keep traveling, carrying information across expanding space, and future minds, human or otherwise, will look up and ask their own questions. Perhaps they will inherit our refined theories and push them further. Perhaps they will discover something we cannot yet imagine. This is not uncertainty to fear. It is continuity to trust. An unfinished universe is not a broken one. It is an open one. And openness is what allows meaning to keep unfolding. As we rest within this understanding, we can let go of the need for absolute conclusions. We do not need the universe to be simple, to feel connected to it. We need only to recognize that we are part of its ongoing story. The atoms in our bodies were shaped by stars. Those stars were shaped by galaxies. Those galaxies emerged from the early universe, now being revealed by James Webb. There is no separation. We are not observers standing outside the cosmos. We are expressions of it, briefly aware. And in that awareness, there is peace. The universe does not rush us. It does not demand certainty. It invites attention. So as this final chapter settles, we allow ourselves to rest, to accept that understanding does not need to be complete, to be meaningful, to appreciate that every answer is a doorway to deeper curiosity. And perhaps that is the most restful thought of all. We live in a universe that is still becoming, still explaining itself, still unfolding. There is no need to hurry. The stars will wait, the light will arrive, and the story will continue, quietly, patiently, just beyond the edge of what we know. For now, we close our eyes, not on an ending, but on a pause, a gentle pause, inside an unfinished universe. As our journey gently comes to rest, there is nothing left to solve, nothing left to fear. The biggest stars ever found do not ask us to remember numbers or names. They ask us to remember scale and calm. They remind us that even the most immense forces in the universe move without haste, that creation does not rush, that endings are not failures, but passages. Somewhere far beyond our sky, stars are still growing, still glowing, still preparing to become something else. And here, on this small, quiet world, you are free to let go of the day. Let your thoughts drift outward, past planets and dust, past glowing giants and fading light, until everything feels spacious again. There is no need to hold on. The universe has been changing for billions of years, without ever losing its balance. It will continue, steady and patient, long after this moment has passed. So allow your breathing to slow, let the silence deepen, and rest in the knowledge that you are part of a cosmos, where even the largest stars learn, eventually, how to let go. Good night.